Alright, so for example, when we get a structure like CCl4, the Lewis dot structure will help you predict this, but you should remember that carbon with 4 bonds is going to be sp3 hybridized, and that is going to have this tetrahedral structure. So at the carbon center, this is tetrahedral and it is sp3 hybridized. At the chlorine center, it is still sp3 hybridized, but it is linear. It is linear. The only difference between these two is that they both have the same hybridization, but carbon has 4 sigma bonds or 4 single bonds, therefore it's tetrahedral, whereas chlorine has only 1 single bond and 3 lone pairs. Therefore, even though it is sp3 hybridized, it is going to have a linear structure. So remember that. Alright, so a lot of examples of these VSEPR theories applied to molecules that can be used to predict their shapes. So for example, CS2 has a linear shape, and how would you predict that? So first you will go ahead and write carbon, which is a central atom, and then you will connect 2 sulfurs, and you know that sulfur is supposed to have 2 bonds, therefore you'll get double bond on the sulfur. So you'll do that, and sulfur is in the same group as oxygen, so if you have 2 bonds for sulfur, then you're supposed to have 2 lone pairs. You're supposed to have 2 lone pairs on the sulfur. And if you look at sulfur, it has 1, 2, 3, 4, 5, 6, 7, 8. So sulfur has an octet, this sulfur also has an octet, and as long as carbon is concerned, again, so 1, 2, 3, 4, 5, 6, 7, 8, so carbon also has an octet. So this is the structure of carbon disulfide, CS2, and you can see that carbon is not going to have a lone pair, therefore you will have a carbon which is sp hybridized, and it is going to be a linear structure. So that is how you would solve the problem. And same thing with hydrogen cyanide, HCN. So if you're given a structure like this, you will draw the central atom, which is carbon, and then you will have nitrogen on one side and hydrogen on the other side, and nitrogen should have 3 bonds and a lone pair. That's what you do. The moment you do that, you will realize that carbon has met its valency of 4 as well, and carbon here is sp hybridized, and this is going to be a linear structure as well. And you might try the other possibility, so you can put nitrogen here, and if you want to give nitrogen 3 bonds like that, then you cannot have a hydrogen on the nitrogen, and if you do that, then that might be a possible structure, but it's going to lead to a situation where you'll have a positive charge on the nitrogen and so on and so forth. So this structure is not going to be very easy or that viable. I'm not going to say this is not possible, but it is not going to be the simplest structure. You can get a simpler structure by just writing it the way it is here. These kind of structures, I will again talk about this a little later. This is possible, but you need to know a little bit more about how to assign formal charges and so on and so forth. So for now, for HCN, stick to this structure. So here's an example of a trigonal planar structure. So for example, if you're given like say COCl2, and if it is said that the carbon is the central atom, add a carbon, add an oxygen, and the simplest way to deal with this kind of structure is give as many bonds to carbon as possible. So chlorine, we know, is in the 7th group, and chlorine, fluorine, bromine, and iodine, they all have only 1 bond. So chlorine's valency is taken care of here, and of course you're going to have 3 lone pairs on the chlorine. Oxygen, as we know, typically has a double bond, and it also has 2 lone pairs, so put that in. Now see if the valencies are met. As long as chlorine is concerned, yes, it is met. 1, 2, 3, 4, 5, 6, 7, 8. As long as the oxygen is concerned, its octet is also taken care of. 1, 2, 3, 4, 5, 6, 7, 8. And as long as the carbon is concerned, its octet is taken care of. 1, 2, 3, 4, 5, 6, 7, 8. So we get the structure, and once the Lewis structure is achieved, you can now see that carbon has a double bond, the central atom. So this is sp2 hybridized, and you also know that this is trigonal planar. It is trigonal planar, and that's pretty much all you need to do. So this is an example of the carbon with an sp2 hybridization. That is a good example of a trigonal planar structure. Alright, so here's an example of tetrahedral structures. So tetrahedral structures are going to have simply these 4 single bonds, as we just saw. So CH4 is one of the good examples which we have seen very frequently. After you draw your Lewis structure, you see that carbon has 4 bonds, so that means it is sp3 hybridized, and the molecule is going to look like that. SiCl4 is same as CH4 because carbon is in the same group as silicon. Silicon is also going to have 4 bonds, and you know that chlorine is going to have a single bond, so you do that. And this is the Lewis structure, and the real structure of silicon tetrachloride is going to look like this. So this is also an sp3 hybridized center, except it's not carbon, it's silicon, and it is also tetrahedral. And you can look at sulfates and chlorates a little later into the semester. Alright, so example of bent structure. So if you are given, say for example, OF2, oxygen has to be the central atom because it is present in smaller number, and the Lewis dot structure of OF2 is going to look like that. Fluorine we know has to have 1 bond, and fluorine will have that, and oxygen is supposed to have 2 bonds, so it will have 2 bonds and 2 lone pairs. And a structure like this is a Lewis structure, and you know that when you have oxygen with single bonds, it's going to be sp3 hybridized, and the oxygen, as you see here, is here. You have these 4 pairs of electrons, but these are lone pairs, these are not bond pairs, so you're not going to consider that as part of the complete structure. It's only these 2 that matter. Therefore, even though this is a tetrahedral structure, since these are not considered as part of the hard group, this is now simply a bent structure or a V-shaped molecule. So that is what water is, OF2 and SCl2 are also. And trigonal pyramidal, we have seen many structures of this. So for example, if we take PF3, phosphorus is going to be the central atom. Phosphorus is in the same group as nitrogen. That means it will have 3 bonds, it will have a lone pair, and here we have 3 fluorines, so each fluorine is going to have only 1 bond. So that's what you would write, and since you don't see any double bonds here, all 3 positions are taken by fluorines which will have a single bond. This is going to be a pyramidal structure. Pyramidal structure, so it looks like a pyramid as you see here. Now if instead of PF3 you are given a structure that is, let's say, POF, let's say it's POF. Now what you need to do, and if it is said that phosphorus is the central atom, you will write phosphorus, and then you have oxygen on one side, you will have fluorine on the other side, and phosphorus, maybe before we do that I want to first make sure that oxygen gets double bond. So take care of the peripheral atoms. Oxygen is usually 2 bonds and 2 lone pairs. Fluorine is only 1 bond and 3 lone pairs. So phosphorus, like nitrogen, likes to have 3 bonds, but here since oxygen needs 2 bonds, you're going to have a double bond on one side, a single bond on the other side. So phosphorus now has 3 bonds, and as you know, phosphorus is also, like nitrogen, going to have a lone pair. So now we have a double bond, which means phosphorus is sp2 hybridized, and since it's a double bond, we are not going to have a linear structure. It's sp2 hybridized. That means it is going to be planar structure like that, and so you have fluorine, you have an oxygen. But since this is not a real group, we are not going to imagine this. That means you have bent structure. You have a bent structure, right? That means this is a bent structure. So yeah, I started to talk about this as a trigonal planar, so that you can see how it's very similar to nitrogen. But then, since this is not a real group, you're going to consider only these two bonds, and that is why it is a bent structure.